Thanks. Thanks to the organizers for inviting me and organizing this wonderful workshop. Yeah, it has been great. Okay, so I'm going to talk about relative survivable network design, and this is joint work with Chaitanya and Jeff, both of whom are at University of Waterloo. Okay, it's gone, right? Okay, yeah, I don't really want to shout. Sorry, can you hear me? So can you hear me? Yeah, okay, all right. Okay, so in network design problems, we are basically given a graph and edges have costs, and the goal of the problem is to pick a subgraph of minimum cost which basically satisfies some connectivity requirements. Okay, and I'm sure you have seen some network design problems. For example, the minimum spanning tree, in which you want to pick a subgraph which is connected, or the minimum cost flow problem, in which you are given two vertices S and T and an integer k, and you want to find a subgraph such that you can send, basically there are k-edge disjoint paths between S and T. Okay, and in general the complexity of the problem is dictated by the connectivity requirements. Okay, so for example, in this case, both minimum spanning tree and minimum cost flow problems, they can be solved in polynomial time. Okay, so yeah, these are well-known examples. I'm sure all of you have seen this. Okay, so in survivable network design problem, it's a special class of network design problem in which connectivity requirements are given as basically requirements between pairs of nodes. Okay, so for every pair of node you have a requirement, an integer RUV, and the goal is to pick a subgraph such that for UV you have RUV as disjoint paths between U and V. All right, yeah. Hello, can you hear me? Yeah, good. Right. Great. So in survivable network design, we have an integer between for every pair of vertex, and that basically tells you how many edge disjoint paths should exist between these two vertices in the subgraph that you pick, right? And this is a fairly general model, and it captures many interesting network design problems like Steiner forest, k-edge connected subgraph, min cost flows, and so on and so forth. And in general, this problem is NP hard. Actually, this is also APX hard. Like, you can't get a pitas, like arbitrarily close to 1. All right. So, okay. Yeah. So a network design problem, you can view survivable network design problem as basically picking a subgraph which is tolerant to failures. All right. So if you fix any two vertices U and V, then what you are essentially saying is that irrespective of hello, yeah. So one view of survival network design is basically a view of fault tolerance. Okay, so basically, if you look at any two vertices u and v, then what you want is that irrespective of failure of any RUV minus 1 edges, less than equal to RUV minus 1 edges, u and v should remain connected in your subgraph, right? And okay, so okay, all right. And in the standard network design, survival network design, suppose you are given an input graph in which, let's say, UV min cut itself is less than RUV, then you know that there cannot exist a feasible solution to the problem, right? So the standard approach in this case is basically to just output infeasible and ask the whoever asked you to build such a network that, okay, it can't be built, and you basically change your connectivity requirements or whatever, okay? So basically we'll come back to this point later. Okay, so there is another view of network design which is called the cut requirement view. So this connectivity requirement, you can basically ask for connectivity requirements, instead of saying that, okay, I want so much connectivity between pairs of vertices, you can ask that, okay, I want these many edges across a cut, right? And so basically it's a cut covering problem. For example, so basically how do you define your requirement for a cut? So basically you take a subset of vertices and you look at all pairs of UV such that one endpoint of the pair is in S and the other endpoint is not in S, and basically you take the maximum for RUV over all such pairs, and you define your f of S to be equal to that quantity. And it's not too hard to see that SNDP, your survival network design problem, is essentially equivalent to finding a network in which across a cut S you have Fs edges, right? This is by Menger's theorem, okay? And again, like in the standard if you have a cut in the graph G such that the number of edges going across that cut is strictly less than the requirement, then you basically output infeasible and just end, right? So the main point of this talk is, okay, if you have small cuts in the graph, right? So I will denote these kind of cuts as small cuts. Then I don't want to just output infeasible, right? Maybe there are only a few small cuts in the graph. I would still want to output a solution, okay? And so how do I basically capture that? Okay, so all right, so here is in case you have in case your graph G is not properly connected, then you can define a relative version of the problem. Okay, so this problem was introduced by Denitz et al. A couple of years ago, and I'll come back to that later, but let me just define the problem, okay? And again, as survival network design, you can define the problem either in a fault tolerant manner or in a cut requirement manner, okay? So first I'll try to define it in a fault tolerant manner, okay? So suppose again you are given some connectivity requirements, and there is basically there is a UV cut of size less than RUV, okay? So assume that this is true. So in fault tolerant model, what we will say is the following. You want to pick a subgraph H such that if you fix any two vertices U and V, and you fix any set of edges F of size strictly less than RUV, okay, then if U and V is connected in G minus F, right, if you remove those edges and U and V are still connected, then I want that U and V are still connected in H minus F, right? Okay, so it's a relative thing. So for example, in the standard model, when you remove small cuts, UV will always be connected in G minus F, right? So in that case, we want that UV is always connected in H minus F, right? But here I'm not saying that. I'm saying that if you have a small cut, like if there are a small set of edges which separate U and V, then I don't want you to basically, I mean, I can't expect you to have connectivity in H minus F, right? So any questions? Like this is like the main definition. Yeah?
Will you allow multiple edges between any two nodes?
Yeah, it does not matter. You can allow that. Yeah, but let's assume that that's not the case for the talk, right? Okay. So is this clear? Like what we are saying here, right? Yeah, right. So basically, earlier I said that you want to pick a subgraph which is fault tolerant, right? So if you remove a certain set of edges, then I want the graph to like U and V to be connected, right? But here I'm saying that you can't expect that if U and V are not connected even in your original graph, right? Okay, so if in the original graph, if you remove a set of edges and U, V are disconnected, you can't expect them to be connected in your subgraph that you pick, right? So that's all I'm saying, right? Okay, I'm saying that if they are connected in the original graph after removal of those edges, then they better be connected in the subgraph that you have picked. All right. So this is the relative version of the problem. Yeah.
This means that you fix the small parts.
Right. Yeah. So all the edges of the small cut should be in the, yeah, right. So you can just pick them in your solution. Yeah.
You have a question on the previous slide.
Yeah.
Is that function little submodular?
No, this is not submodular. At least the way as it has been defined. It's I'll come back to that. It's called weakly supermodular. Supermodular. But it's not even supermodular. It's weakly supermodular. So yeah, this one is always weakly supermodular. Yeah.
Are the edges capacitated?
Yeah, edges are capacitated. Yeah, like they have cost. So capacity is one. The cost can be arbitrary. So if you pick an edge, it will contribute one to the requirement of the cut, but its cost can be arbitrary. So this is a relative version coming from the fault tolerant view, and you can also come to the relative version from the cut requirement view. Alright. So in the cut requirement view, what you can ask is, okay, so across every cut, you should have min of f comma s comma delta g of s edges, right? So basically, you want to pick a subgraph such that across any cut, across any subset S, you have minimum of fs comma delta g of s edges. And if you have a small cut, then basically I'm asking you to pick all the edges from that cut. All right. So basically, okay. So basically, we can define a relative version of the standard classical network design problem in two ways, and it turns out that these two versions in the relative sense, they are not equivalent. Okay, in the standard network design, these two problems were actually equivalent to each other, but in relative world, they are not. Okay, but before that, okay, so we can write a simple linear program for cut RSNDP, right? It's just you want to, so you have an indicator variable xc which takes value between 0 and 1. And you want to minimize CEXC, like total cost of edges picked, and you want that across every cut, you have at least min of fs comma delta gs edges. That's it. Okay. So coming back to cut requirement versus fault tolerant view for relative SNDP, they are not equivalent in, okay, as opposed to the classical network design problems. All right. So to see an example, so we have S and T, and S and T have a requirement of 2. Okay, and all the other pairs of vertices have a requirement of 0. So basically, it's a single demand kind of thing. Okay, so the cut RSNDP will pick all the edges, right? Because yeah, so basically, if you look at any cut like this, it's so basically the demand is basically min of 2 comma delta g of s, which is again 2. So basically, I will pick all the edges across this cut. So the cut version will actually pick all the edges of the graph, but the fault tolerant one will only pick the ST path. That's the only thing it needs to pick to satisfy the requirement, right? So Yeah, and you can verify this from the definition. So basically, what do we need to verify? That the ST path is a feasible solution to the fault tolerant version. You just need to pick an edge, and you want to say that if I remove this edge, any edge, then if it is connected in G minus F, then it is connected in H minus F, and you can verify that easily. All right. So okay, so the cut requirement and fault tolerant views are not equivalent in this case, but how far are they? But still, is their complexity the same, right? Like, can you still get the same kind of approximation results for both of them? Okay, and unfortunately, it turns out that in this case, the fault tolerant thing is much more complicated than the cut requirement thing. Okay, okay, but before that, let me say one more thing. Okay, so we say that a set is fully connected if the induced graph on the set and its complement both are connected. Okay, so you might know this as bonds also in graph theory. Okay, so you can actually write the linear programming relaxation for fault tolerant RSNDP, okay, as follows. So what you do is basically you only enforce the condition that the sum of the edges going across a cut is at least min of fs comma delta g of s for fully connected sets. All right. So instead of enforcing this condition for all sets, you only need to enforce this condition for fully connected sets. Okay. Right, and this will capture your fault tolerant RSNDP. Okay, so you can see that in this case, we will not enforce for a fault tolerant version of the problem, we will not enforce the condition for this red cut, right? Because this cut is not fully connected, right? If you look at the right hand side of the cut, it has two connected components, right? All right. Okay, so what is our result? So we basically look at cut RSND, and we show that the integrality gap of the LP relaxation for cut RSND is at most 2. All right, good. Okay, so a few words about relative SNDP. So this problem was first introduced by Dimitz, Corentin, and Kotsas in 2022, and so basically they first introduced this relative version, like this fault tolerant version of the problem, and they also gave a LP for the problem. Okay, but unfortunately they did not realize in their paper that these two versions they are not actually equivalent, like they are different versions. Okay, and they also showed how to solve the linear programming relaxation, so they gave us separation oracle for this problem. Okay, so yeah, so while we were working on this problem, we were just looking at the cut version of the problem, the cut requirement version of the problem, because we thought that both the versions are sort of equivalent. So if we solve this, then we also solve the other one, and we solved the cut version, and then we were very happy. But then, but then we realized that okay, this actually does not solve the other problem. Like the other problem is actually much more difficult. Yeah. Okay, so in a follow-up work along with the authors, along with Nutov, they gave a 2 to the power k squared approximation algorithm for the fault tolerant version. Okay, when there is a single demand, like you just have S and T, and you want to find a subgraph which has k as disjoint paths between S and T. Okay, so even for the single demand case, we don't know a constant approximation algorithm. Forget about constant, like we don't know anything better than 2 to the power k squared, like even a log k would be, or a k would be very interesting. All right, okay, so any questions till now? Okay, good. All right, so in the rest of the talk, I'll try to give a brief overview of the proof, how we prove this result. So I'll have to introduce a few notations. Definitions. So we say that a function is weakly supermodular if so if the function value on the empty set and the full set, that's 0, it's symmetric, and basically fa plus fb is less than equal to max of fa A intersection plus F A union B plus, or F of A minus B plus B minus A, right? So in weakly supermodular, we want that FA plus FB is less than or equal to one of those, and instead of being supermodular where we want it to be less than or equal to both of them. Okay. And it's a well-known fact that the function for survival is weakly supermodular. It's not very hard to verify that this is true. Okay. And so we will need another fact that if F is weakly supermodular and H is submodular, then F minus H is weakly supermodular, right? I mean, just follows from the definitions of submodular functions. Okay. All right. So, okay. So what is known about this problem? So for the standard network design problem, this is the LP. So basically you want to minimize the cost of the network given the cut requirements. So Jan actually gave a very nice two approximation algorithm which started this whole area of iterative rounding. So what Jan showed was if you look at any vertex solution, any feasible vertex solution to this problem, then you can actually argue that there is at least one edge in the solution which has a value of at least half. Okay, so you solve this LP optimally, you find a vertex solution to this LP, and you can show that there exists a edge with value at least half, and then you can basically set this edge to be equal to 1, and hence you lose a factor of 2 here. Right, and then you can actually continue like this, right? And overall, you will get a factor of 2. Right. So Jan showed that if F is any weakly supermodular function, you can the above LP has a integrality gap of at most 2. Okay, and we will actually prove an analogous result. Okay, so our result is the following actually. So if F is any weakly supermodular function, then if the cut requirement is basically min of F comma delta of G, then you can get an integrality gap of at most 2, right? Okay, good. And we basically follow Jan's technique. So we will show that there exists in an extreme point, solution, there exists an E such that X star E is greater than or equal to half, right? We will follow the same technique, okay? But you should notice that this min of Fs comma delta G of S, this function itself is not weakly supermodular. I mean, if it was weakly supermodular, we could have just used Jan's result, but this is not weakly supermodular, right? Because if you look at two sets, let's say there are two sets S and T, which are not small, right? They are like, they're not small sets, they are large sets, okay? And, but it can happen that one of S intersection T or S union T is a small set, right? And then your inequalities won't hold, okay? So in general, this particular function is not weakly supermodular, all right? Okay. Good. Okay. So as I already said, a cut is small if f of s is okay. So if f of s is greater than delta g of s, and let E1 be the set of all edges that belong to a small cut, right? And it's clear that the LP will put a value of exactly 1 on all the edges of a small cut, right? So you can safely put all the edges of a small cut in your solution and basically construct a residual instance, right? So you basically remove all the edges of the small cut from the graph, and you basically update your cut requirement function by subtracting f delta of E1 from the thing, right? And so from now on, basically, we will work with this graph, where if there is a small cut, then it's basically empty, like there are no edges going across this particular small cut, right? Because we have already removed all the edges of the small cut and updated my function value. Okay, good. Any questions here? Yeah. Yes, you can actually, okay, let's not get into that, but I think, okay, in the SNDP, the standard SNDP version, in the standard SNDP version, you can check it, right? Survival network design version, like if you have requirements and stuff. Yeah, for general weakly supermodular function, we will have to assume separation oracle, right? Yeah, but in general survival network design, you can do this by computing max flows and stuff. Yeah. But in any case, so you have a separation oracle for this particular LP, which was given by them, right? And you just look at that separation oracle, and these edges will have a value of 1. Like once you solve the LP once, like these edges will have value 1, and you can just update your graph from there, right? So you don't need to do that. Okay, all right. Any other question from now? Okay, from here. Okay. So basically, we now have a graph in which all these small cuts are empty. Okay, and we have a weakly supermodular function, and we want to show that this particular LP has an integrality gap of at most 2. Good. Okay. Okay. So here is the proof idea. Okay. So the proof idea is to basically split the instance into 2 parts, right? So what I will do is I will consider a set. So okay. So let A be a set which has the maximum deficiency. Okay, so A is the set which maximizes fs minus delta g of s. Okay, so the idea would be to basically split this particular function into 2 functions, one which is defined on A and the other one which is defined on the complement of A, right? So in other words, what I'm going to do is I'm going to get rid of the cross constraints, sets which are crossing both A and its complement. Okay. So let B be the complement of A, and we define two smaller functions, fa and fb, as follows, right? So to define fa, we take a subset of A, and we define fa of s to be equal to fs, maximum of fs and f of A minus s, and similarly we define fb of s, and you can basically set empty set and the whole set value to be equal to 0, and by definition this is symmetric, and it's not too hard to verify that this particular function as defined, they are also weakly supermodular, right? Okay, good. Okay, good. Okay, so you can show that these 2 functions are weakly supermodular, and so we had a solution x star for the whole problem. Let x star A and x star B be the projection of x star onto A and B, right? Remember that there are no edges going from A to B, right? The cut A comma B, that is empty, so all the edges, they are either both. So basically all the edges have both their endpoints either in A or in B, right? So you can easily define a projection x star A and x star B, right, of the solution x star onto A and B. And again, it's very easy to verify that actually these 2 solutions, these 2 projections are actually feasible solutions for LP on the induced subgraph on A with function value fa, and induced subgraph on B with function value fp. Okay, so this is clear. Like this is important, yeah. All right. Okay. So we start with a vertex solution to the original problem. I look at a curve of maximum deficiency. I define these 2 functions on subsets A and B, and my original vertex solution, original feasible vertex solution, is also a feasible solution for this for these 2 smaller problems. Okay, but I want to use induction, right? And so I just know that if it was a vertex solution, x star was a vertex solution for the whole thing, then it's a feasible solution for these 2 smaller instances. If somehow magically we could prove that this was also a vertex solution for these 2 smaller problems, then we could inductively argue that okay, our induction hypothesis will be like for any feasible solution there is a x star with value at least half, so I could just use induction on one of these 2 things, right? So that would be the idea. So what we would try to show is that a vertex solution, if you project onto A and B, then x star A and x star B, they are also vertex solutions for FB and FP. Okay, and to do that we will basically show the following. Okay, so if XA and XB are the feasible solution for these smaller problems, then if you take the union, then this will also be a feasible solution for the bigger problem. Okay, is this making sense? Like, any questions here? Okay, right. All right, so I'll try to sketch a proof of this. So a complete proof of this, and this has some case analysis and stuff. So I hope, yeah. Okay, so let's assume that there is a set T which is violated, okay, which is not satisfied. So I have a feasible solution XA and I have a feasible solution XB, and I'm just taking their union. So yeah, so maybe there is a set which is crossing both A and B which is violated because, yeah. Okay, and I'll use this notation when I say X of S, then it simply means the sum of all the X values across this cut S. Okay, so F is a weakly supermodular function, so F minus X, since this X of S is a submodular function, F minus X is again a weakly supermodular function. Okay, and recall that T cannot be a small cut cannot be violated by definition because a small cut is empty, and there are no edges going across A. Like, since A was a small cut, it's empty and X of A is equal to 0. Okay, so basically, so we know that weakly supermodular inequality holds for A and T. So if we write down the weakly supermodular inequality for A and T, so FA minus XA plus FT minus XT, that would be less than equal to max of two quantities. So I'm going to assume that the equality holds for intersection and union. Okay, so FA plus FT minus XT, this will be less than equal to FA intersection T minus XA intersection T plus F of A union T minus, yeah, X of T union A. All right. Okay. So basically, there are three cases to consider. Right. So is anybody following this, or am I just okay? Maybe I'm wrong diagram here. And yeah, and T is basically this set. So I know I have a feasible solution for this instance and this instance. I want to say that I also have a feasible solution for the whole thing. So a set which could be violated has to look like this, right? And yeah. All right. So, okay, so the first case is that A intersection T and A union T both are small cuts. All right. And in this case, it's not hard to argue that, okay, so remember, we cleaned up our instance and we removed all the edges of small cuts. So in this case, A intersection T and A union T, they are empty basically, right? These cuts are actually empty. And A is also empty. So in this case, basically, one can argue that actually T is empty because A intersection T is empty, A union T is empty, A is empty. So basically T has to be empty, right? And if T is empty, then T is a small cut, and that is a contradiction. It can't be violated, all right? Okay, so the other case is A intersection T and A union T both are not small cuts, right? Okay, and in this case, again, if they are not small cuts, then for the smaller problems, I have a feasible solution. So F of A intersection T minus X of A union T. By definition of FA, this is less than equal to FA of A intersection T minus XA union T. So this is less than equal to 0. So both these terms are less than equal to 0. And so again, we get a contradiction because the right hand side is less than equal to 0 and the left hand side is strictly greater than 0. Okay, great. So yeah. So these two cases are fine. Note that in these two cases, we have not used the fact that A is a cut with maximum deficiency, which we will use in the third case. So exactly one of A union T and A intersection T is a small cut, okay? And in this case, since A is a small cut with maximum deficiency, it must be true that F of A is greater than equal to F of A intersection T minus X of A union T intersection T, right? So I'm assuming A intersection T is small. And since FA is the cut with maximum deficiency, this inequality holds, okay? And if this inequality holds, then, and we also have this inequality that I have stated here. So this basically implies that F of A union T minus X of A intersection T, this will be greater than equal to Ft minus Xt, and which is strictly greater than 0. And if this is strictly greater than 0, then it simply means that either, yeah, so Okay, so f of a union t is actually equal to f of b minus t, and this is less than equal to fb of b minus t just by definition of fb, and x of a union t is again this is equal to xb of b minus t, and this basically contradicts the fact that fb of a union t is sorry, it contradicts the fact that a union t is not a small cut, okay, and this gives you a contradiction. All right, so basically the main point of this whole thing, okay, if you didn't follow all the analysis and all those things, was that so I'm given some connectivity constraints for all subsets of this ground set V. What I'm able to do is basically I'm able to drop the cross constraints and construct two smaller instances defined only on A and only on B, right? And somehow the feasible region for both these problems are exactly the same, right? So in this sense, I'm able to make some progress, right? Okay, and yeah, potentially this idea could be useful elsewhere also, right? All right, so I guess this is all I have to say. So the main open problem here is like, can we get a constant approximation even for the ST one demand case where you have two vertices S and T and you want to, yeah, find case connected, case disjoint paths between S and T. Okay, and we are hopeful that some of these ideas can be used to make some progress on like a new class of network design problems that have come up in the past 5-7 years, and that's all. Thank you.